I want to bring to your attention this problem. It's problem 5C9. Okay, so 5C9 is one of the problems that I suggested you to watch. It's on page 350 on the book. And this problem also has tricks. So we have a rod of mass m and of length L, and it's pinned to a block of mass m. Okay, so this word pin is important. And then we see the block can slide on a frictionless surface. And we see that the system is released from rest at an angle. All right? So we have the block can slide on frictionless surface, and the bar and the rod and the block are released from rest. And we're asked to find the angular velocity when we reach 90 degrees as measured from here. So when the bar is here. And the velocity of point A. And then, this explicitly is telling us to combine work energy and linear impulse momentum. So let me tell you why. And this is the important part of this tutorial. The reason why this is important is the following. Or maybe, do you guys see any similarities between this block and bar combination or block and rod combination and the problem that we did of bar and disc combinations? Is there anything that is similar? Nothing similar? What is similar, or what is different then between the two? Nothing. So let me make this drawing. This is the system that we were considering before. Is there anything, what is the main difference, let's say, between, maybe main difference is a strong word, but what is different between this system and this system? Is rotated, okay, yeah. This guy is kind of going to move down, but this one is also moving down, so that's a difference, yeah. Yes, so one important difference is that the problem 1 has a fixed point. Exactly, and this problem doesn't have a stationary point. That's very important. And what other key feature do you guys see from problem 1 and example C9? In this case, is the same type of feature. It's something extremely, extremely important, and it's the key. The block and the disk are only translating. Well, certainly the block and the disk Uh, well, yeah, let's say that that's a similarity. You're getting close, but there is something else that is similar. Okay, so let me just then give it up. The bar okay. So if I put my ugly observer over here and my observer over here, we see that there's going to be relative motion between the two. So once more, there is internal motion into our system if we draw a bubble around it like this. Okay? And that type of situation, when there is internal motion, leads to the need of use of impulse momentum equations, one of the two, and work energy. So then the strategy is to use this combined work energy linear impulse momentum, because there is relative motion inside our system, inside our, let's call, control volume, that I refer to typically as system size. In the videos, it's referred as that. And this is the most important thing that is going to tell you, wow, sorry, that is going to tell you when do you use, in a combined way, work energy and angular or linear impulse momentum equations. Now, if we use work energy or impulse momentum equations, we want to treat the system as a whole, right? To begin with. Now the question is, okay, and here is the free body diagram. So the free body diagram is not too hard. Now the key question is, okay, we know that we need to use impulse momentum equations, and we can go and find each of the components here. I'm going to let you guys watch the video and do that. But to solve the problem, we need to ask ourselves, why linear impulse or why angular impulse momentum? And in this problem statement, we were told that the answer is, for this problem, we need to use linear impulse momentum. Whereas for problem P1, it was angular impulse momentum. So can we decide by looking at these two drawings why on the top one we needed angular impulse momentum and not linear impulse momentum? There is something that is going to straight away tell us why. And that is that in this problem up, we had, the system was fixed as a whole. I mean, there was a point that was never translating. Point A was fixed, and then this point never moved. Okay? So if there is a point that never moves, then you know that linear impulse momentum is not going to be so useful, because linear impulse momentum requires translation. Okay? And then, of course, this system here is going to translate as a whole. There is no fixed point, so it's going to translate. And this is why linear impulse momentum is the tool to use. So you can see this very nicely with this other simulation here. So this is slightly different problem, but we will see that when this rectangle starts to move, the block below starts to translate. So the impulse from this guy, the momentum from this guy is being translated into motion here, and then as soon as it hits it and it changes the direction of the speed, then the block is moving into another direction. So there was another animation of a type of system like problem 5C. It's this one. You see, the disk in here is translating, is rotating also, but this point is translating, and it's changing direction as the bar swings. And this is precisely what happens with this assembly here. So I'm not going to solve the problem, but I think it was much more interesting for me to explain to you guys why linear impulse momentum was a choice, and give you a physical interpretation of why do we use it and when to recognize that we need to use it. So once again, look for what's happening inside your system, and if there is relative motion inside your system, then there is a high chance that you will need to combine impulse momentum equation with work energy equations if you're asked to find velocities or angular velocities or changes in height, changes in angle. And furthermore, we see that if our system doesn't have a fixed point, so use when system has no fixed point, and then this one, if we have a fixed point, then you can use it. When you approach problems, these are the questions that you need to ask. You need to ask yourself to know how to which kinetics to use.